that order. So we have part of the diagonal here, part of the diagonal there, but what happens when this group of genes is inverted? This gene is now here. This gene is now here. And so on. So an inversion is seen like the second diagonal, part of the second diagonal. And we see lots of them over there. Why it is interesting? Well, because, well, for many reasons actually. First of all, it tells us something about evolution. I'll show that on the next slide. Secondly, yeah?
I would like the vertical line next to the first.
The vertical line, I think it's some transposon or something like that. It's a gene that has many homologs. Should be something like transposon. And actually, I mean, we don't see. We have things like that on the left slide as well. For instance, here we have lots of genes corresponding to this one. This is the entire line. Okay, so and secondly, there are some biological processes that rely on these inversions for bacterial life. Again, I'll tell you a story a bit later. Now, what do we have here? We have inversions. Well, we have actually each arrow corresponds to not to a single gene, but rather a group of genes such that there were no breakpoints within this group. It's called the synteny group. Synteny means that there is a part of the genome or a chain of genes or whatever such that there were no no breakpoints between genes from this group. So what happened, for instance, where? Well, to that red gene, which is 6 or 7, 6 from the left. Well, it got inverted in some strains. So in some strains, it is in the direct orientation. In some strains, it is in the complementary orientation over here. Here. That's true. This black thing is never inverted, actually, at least not in the strains from this subfamily. Now let's check what happened. Let's see what happened. Okay, so with this group is invariant, and this group is invariant. But something has happened with this group of light blue, dark blue, and violet genes. So strain number 1, 2, and 6, the order is do you see what I'm writing here? All of you, okay, good. So for strains 1, 2, and 6, the order is light blue, dark blue, violet. For strains 3 and 4, the order is violet in the reverse orientation, then light blue and dark blue. And for strain number 5, it is dark blue in complementary orientation, light blue in the complementary orientation, and then violet. So we have these 3 possible arrangements. Now, what could be, can you infer, well, assuming that, actually each of them could be an ancestral strain, but let's assume for simplicity that 5 is the ancestral strain. What events could have generated these strains or these strains from strain 5? Any ideas?
Well, for the third and for the fourth cases, it's just reverse of the field.
Yeah, the complete reverse. It's a complete reverse. If we just invert this entire sequence, we would say we will have V inverted, L, so we're going in that direction. L is again returned to the, well, not reversed, and D again not reversed, which is exactly as 3 and 4. Okay, and how do we get these guys from 5?
The 16 was for only D and L.
Yeah. So if we just revert these two, then we'll have, well, it's simple to show here. If we reverse L and D, we'll have D reverted, L inverted, and B, which is exactly like 5. Okay, so actually, what has happened here is that there is genome number 5 is in the middle, and then there is 3 and 4. It's one event, or it is 1 to 6 here. And we actually don't know where is the root. I've told you that for simplicity we may assume that 5 is ancestral, but it might easily be that each of these might be the ancestral one. So for instance, this is the ancestral sequence, then we have first the inversion generating 5, and that's the second inversion generating 3 and 4. Okay. So once again, we have 5, 1 to 6 on one side and 3, 4 on the other side. And the history might be like that, or like that, or like that, whatever. Okay, now there is a group of genes over here, starting between this invariant block and which? Whatever. It's actually not invariant, and here. So we have the same group of 6 genes in different order. So it's yellow, orange, red, green, blue, and violet. So once again, what do we see there? For 1, we have yellow, orange, red, and then green inverted, blue, and violet. For 2, we have yellow, then what? Green, red inverted, orange inverted, blue and violet again. For 3, we have violet inverted, blue inverted, green, and red, orange, yellow, all inverted. Red, orange, yellow, all inverted. Now 4 is like 3. 5 is also like 3. And 6 is like 11 percent, yes. Okay. Now for this group of genes, what is the set of events that have generated them? Any guesses?
If you consider the first and the second, there was reversed in ORG pattern.
Okay. So here we have this reversal. Okay.
And for the first and the third, it's just full reverse again.
Complete reversal. Okay, yes. So between this and this, we have just a complete reversal of the entire block. Okay. So now we have one and 6 are in the middle. 2 is different. And 3, 4, 5 are different on the other side. Again, we don't know which of them is the ancestral form, but we know that these operations distinguish them. And we can order them. What's even more important, we can not only put them into classes with the same sequence, but we can also order these classes. Okay. Now, given that these two different regions, yeah?
Can't we find some compounds between?
No. In this particular, yeah. No. Actually, what we can do, we can now make a more detailed.
Yeah, but could they put like several rearrangements that could be from, for example?
Yeah, but that would be it would require much more arrangements. Of course, we can always infer a more complicated story. But if we just take the minimum number of events, we can't do it any other way. No, it's a good question, but in this particular case, all alternative scenarios would require much more events. So that wouldn't be parsimonious. Okay, now, again, to repeat my question, could we now make a more detailed scenario distinguishing all the, not all the traits, but
Well, we see that 1, 2, 6 is on the left, and 5, and 3, 4, 5 on the right,
okay.
including the sensor.
Okay, actually, let me rewrite it. I've just rewritten this, but in a more, well, as a hint. So basically, we do know now what has happened. Because to distinguish between 1, 2, and 6, we use this scenario. And to make more detailed story about 5, 3, and 4, we took this one. So actually what has happened is that. And again, we don't know who of them is the ancestor. But we do know what might have happened and in what order. And basically, this is just well, small, teeny part of like 6 genomes and 10 less than 10 genes. But we can do the same type of analysis on complete genomes and reconstruct the history of rearrangements in these genomes. And this is what people do. And there are some, well, actually that's an interesting story because at some point people believed that this type of analysis would be much more sensitive and much more reliable than analysis of substitutions. And the idea was that the problem with constructing phylogenetic trees with nucleotide or amino acid substitutions is that when we are close to saturation, when we see lots of events occurring in the same position, all our tree reconstruction methods become confused. I mean, maximum parsimony fails first because maximum parsimony explicitly requires absence of parallel events or consecutive events in the same position. And at some point, other methods also become not very reliable. Whereas for inversions, the people thought the genomes are huge. It's highly unlikely that the same point would be used several times for inversion. The genome would be cut at exactly the same position, which means that all events are unique and the resolution power of our methods based on genome rearrangements would be great. In fact, it didn't happen. And we actually already had seen the reasons for that even in this simple slide. It didn't happen because actually the breakpoints of inversions are reused. They might be used in several different events on several different lineages. And this happens because these inversions often happen when there is a repeat. When the end of the reversions are actually the same sequence, highly similar sequence. And so that means that each transposon, each multi-copy element, or I don't know, ribosomal RNA or whatever else, might be used several times in different combinations. So the problem here is that the inversions occur not at random points in the genome, but rather in the regions which are copies of the same repeated sequence. Okay, but anyhow, this is doable and interesting. The dot plots, well, they might be sort of complicated. They occur not only in E. coli and Shigella, but also, for instance, here in Dermatoga strains. And this is related actually to this issue of genome inversions in bacteria is linked to many nice, lots of nice biology. Because the inversions are not neutral actually. The point is that well, one of the simplest manifestations of this is as follows. We as computational biologists think about the genome as about string in our computer. In fact, it's a molecule. It is involved in lots of processes, and the most basic of these processes is replication. Let's assume that replication starts here. Now there is the leading strand. Okay, it's bad color. Let's take a breath. Until the terminator of replication. And there is this second lagging strand. So this is leading, and this is lagging. Now, if we go on the other side, this strand, oops, sorry, wrong color again. This strand would be leading, and this strand would be lagging. Is it clear? So we have two replicors, and in our computer now, and suppose this is the random point, which is position number 1 in our genome. So what do we have in gene bank is it starts with the leading strand, then we have the lagging strand, again a part of the leading strand. And the leading and lagging strands are not equal. First of all, genes, and especially highly expressed genes, prefer the leading strand. So basically what we see is that highly expressed genes are here and rarely here. Why so? Because when replication occurs, transcription doesn't stop. RNA polymerase is faster than the replication fork. So when the replication goes in this direction, if transcription goes in the same direction, the polymerase meets the replication fork and then just stalls. I mean, nothing bad happens. It's like a head-to-tail accident on the road. It's bad, but not terrible. Now, if the gene is transcribed from the lagging strand, it's head-to-head collision, which is really bad. Nobody cares much about transcription because, I mean, transcription is a cheap process. Like, polymerase is thrown out of DNA, well, it would start again in a couple of seconds. But replication fork actually consists of lots of different proteins in specific information. And if something goes wrong with the replication fork, it stalls, and it's actually like lots of machinery is then involved in repairing this stalled replication fork. So head-to-head collisions are really bad. And in evolution, I mean, selection forces highly expressed genes to reside on the leading strand. That's one story. And we actually do see it. If we take in many bacterial genomes, we see that like 3/4 of genes are on the leading strand and only 1/4 is on the lagging strand. And even if it's 50-50, it's still likely that highly expressed genes will be on the leading strand and weakly expressed genes on the lagging strand. The consequence of that is that not all inversions are equal. So again, if we have this what happens if inversion occurs here? Well, the former leading strand is now lagging, and the former lagging strand is now leading. So we've done everything wrong. What happens if inversion occurs here? Well, basically nothing. Because if we invert this fragment, this part becomes this part, so it's still leading. This part becomes this part, and it's still lagging. So nothing has changed basically. And what we do observe is that these symmetrical inversions occur much more frequently than non-symmetrical ones. Actually, I have a slide somewhere there, but just believe me for a moment. One more difference between the leading and the lagging strand is that on the leading strand, the genomes prefer G, and on the lagging strand, the genomes prefer C. And that on the top, it doesn't depend on GC contact. So basically what we see much more pairs like that than pairs like that. So again, in our hypothetical case, we'll see, if we look at the single strand, the one that has been deposited to gene bank, we'll see more G's on the leading strand, more C's on the lagging strand part, and then again more G's. Probably it happens because the mutation processes are different for the leading and lagging strands, and this probably happens because the mechanism of replication of the leading and lagging strand is different. The leading strand is replicated continuously. The lagging strand here had these Okazaki fragments, RNA primers, and stuff like that, ligases and stuff like that. And somehow, actually, I don't think anybody knows how, but somehow it creates the difference in the G and C composition of the leading and lagging strand. There's also a difference between A and D, but it's weaker. For GC, it's very well pronounced. And that can be used to predict where are the origins and terminators of replication. So basically what we do, we go over fragments and calculate the number of G's and C's and see whether there are more G's than C's here. Then we shift it again, calculate, count G's and C's, and so on. So here we would have more G's, here we would have more C's, and then again we would see more G's. And the transition region would be exactly our origin if it's transition from it would be terminator if it's transition from high G to low G, and it would be origin if it's transition from low G to high G. There are programs there are databases who do that, there are programs that do that. And this is how it looks like. Actually, it's not a very. Oh, sorry. I should have this somewhere. No? Okay. I have to draw it. So basically, what people do. So the horizontal line would be positioned in the genome. And we would consider fragments starting from position 0 and extending to the position we are looking at. So for instance, here, we would take this entire fragment of the genome and calculate the value which is called GC skew, which is defined as number of G's minus number of C's divided by the total GC quantum. So again, if we start with the leading strand, then we have lagging strand. And then again leading strand. And again calculate the GC skew for extending fragments. Could you guess how the plot would look like? If there is like very little noise. Yes. Presumably you are right. So we'll have, we start with, it's leading strand, so we start with increasing, let's have 0 here for simplicity. We'll have increasing GC skew. Then, after we pass the terminator of replication, we actually start losing G's. So it would, sorry, it would go down. And then when we come to the origin, we would again go up. So this would be the plot of GC skew for the region, for the genome like that. Okay. Now what would happen if we have an inversion here?
Nothing.
And if you think carefully. Okay, anybody can draw it. Any ideas?
Yeah, well, symmetrical.
Okay, go ahead.
Well, along these axes,
And then?
well, and I think we will do this.
Well, but you can have a break.
Yeah, but
If it continues, yeah, but basically you're right.
this is like,
So there will be just a T.
Yeah, it would be an additional peak here. So on this, in this fragment, it again goes up, and then it repeats itself. It goes down and then up. So we'll have an additional peak here. And actually, this is what has happened with these unhappy Kermatoga guys. So we have, at the top, you have the GC skew plot, and you see that it's nicely monotonic in the major part. But then there are lots of small peaks indicating that there has been lots of inversions in that region. And actually, we do see that here on the dot plot, because it's actually the top right region, and we see lots of inversion there. The box, what's called box C, is exactly the region that has generated this pattern with lots of small peaks in the GC skew plot. Okay. Then I don't want to go into the next subchapter, so instead we'll play for some minutes with dot plots. So as I said, if we have just a single conversion, it would look like this subdiagonal on the dot plot. But what if we have two inversions? For instance, if we had the following scenario, it was we had a genome, then we had an inversion here, and then we had an inversion here. How would that look like on the dot plot? Okay. Actually, now I have two questions. First of all, what would be... Okay, Casey. Now... Okay, so can now actually show what inversions correspond to this dot plot? What is the series of events corresponding to this dot plot? Yeah, two small ones. So actually, what has been drawn here is one small inversion and another independent small inversion. Got it? Yeah, of course. If you forget, well, forget about this. Look here. It's just this inversion and that's it. Now look here. It's just that inversion and that's it. But it's not the same thing as here. Okay, now what are the guesses about this one? Okay, could you just remove what was not needed, because otherwise... Okay, yeah. Okay, Yes, indeed. So, our first inversion, this one, is here. So this is what we have after the first inversion. And then, the middle part of that has been inverted once again, and this is exactly what you have drawn. Correct. This is easy. And now comes the troll. And this, as soon as you draw the correct dot plot, I'll let you go. But I won't let you go unless you do this. We take all of them, you'll need them. Okay. Do you agree? Does anybody agree? Actually, it couldn't be like that. For the following reason. On this plot, this region corresponds to two different regions here. So it's not an inversion, it's duplication. Yeah, I mean exactly that. This region corresponds to nothing.
I mean, yeah.
There is nothing in this.
I should.
There is nothing here.
I should have drew the flow.
Okay, go ahead.
That's the same mistake.
Okay, good. You should recall that. Actually, we have seen that already. And this is these two small inversions, one here and one here. And it's not the same thing as here. But, okay, now. That's it. You'll have your two attempts. Vasily and then you. And could you draw vertical lines here? And horizontal lines? Okay, let's see. Okay, thank you. Okay, actually I'll show you how to cheat. It's simple. Let this point be here. Then we have the following regions. We have A, and let this point be here.
Yeah.
B, C, D.
Okay.
Okay, yeah, I see. Yeah. No, the lengths are not important. After the first inversion, we have A, C inverted, B inverted, D, E. After the second inversion, we have A, C inverted, D inverted, B direct, E direct. Oh, I'm sorry, I forgot to let you draw. Sorry. No, over here. Okay, anyhow. So when we have A, B, C, D, A, B, C, D, E here, we start with A. Then we have, here we have the region corresponding to inverted C, which is here, indeed. Then we have the region corresponding to inverted D, which should be here. Then we have the region corresponding to B, inverted D, will be here. And then we have the region corresponding to B, and then the region corresponding to E. So it should be something like that. Once again. This is clear. We first invert B and C, and then we inverted B and D, and get that. Now what do we have here? We start with that. Now, this is the second region here. It's inverted C. Sorry. This here. This is the region corresponding to inverted D. Oops, sorry, I'm doing something terribly wrong. What would that be? No, I'm not doing something terribly wrong. This is inverted C. This is inverted D. This is B. And this is E. So this is how it would look like. So basically what we had this. This is the first inversion. And then when we invert this and this region is inverted and goes here, and this region is inverted and goes here. Okay, well, then probably that's it. See you.